Hey, good afternoon, everyone, and welcome again to another session of Prestress Concrete Design. For today, we will be discussing the remaining prestress losses na nasimulan na natin a couple weeks ago. And then today, after natin i-discuss yung mga losses na yon, we will apply it to an example, a very rigorous example, no? To consider yung mga losses na nabanggit natin before and yung di-discuss natin today. Okay? So, at the end of this session, ito yung ating outline of our lesson. So, the first one is continuation ng losses natin. So, losses due to friction, anchorage setting losses, change of prestress due to bending of a member. And then we have yung applied example natin. Okay? And then as our learning outcome for today, should be able to discuss yung remaining prestress losses. We should also define different formulas na gagamitin natin for the remaining losses na solve natin. And then to solve an applied example showing the calculation of all prestress losses depending kung anong stage of um, loading yung kino-consider natin, no? It may be sa initial, at transfer, or after transfer, or given a um, a particular year, halimbawa, no? After nung pagka-cast, yan yung kailangan natin i-calculate. Okay? So to start, recall lang natin itong table na to because this is our reference kung ano yung mag-exist na losses ko depende sa type of system natin. Again, for pre-tension members natin, we are um, we are expecting na mayroon siyang elastic shortening, relaxation, creep, and shrinkage. No? And then for post-tension members, we have all our losses. Except sa elastic shortening, it will not be present kung simultaneous yung pag-jack natin dun sa dot ng tendon natin. Pero pag sequential siya, that particular sequence, no, yung from start hanggang dun sa n-1 ng number of set ng i-jack natin, will experience a varying percentage ng elastic shortening na yun yung kinoconsider natin dito. And then, same with the pretension members, meron siyang relaxation of steel, then creep and shrinkage of concrete, and then ang meron sa kanya is yung friction and anchorage. Especially, may contact tayo between the duct natin tsaka yung concrete natin. And then for anchorage is yung pinaglalagyan yung ating jacking equipment. Okay? So kung saan nagaantay yung mga tendons natin to be stressed. Okay? So ito yung mga again required losses natin na ika-calculate for a particular beam, no, or a particular section. Okay? So to continue, let's us first start dun sa losses due to friction na tinatawag natin. And a loss of pre-stressing, of course, occurs in post-tensioning members due to friction between the tendon tsaka yung surrounding concrete ducts natin. Okay? Di ba sabi natin, yung mismong tendons natin are enclosed by a duct, no, na siya yung kapag nabuhusan natin, kasi di ba sa post-tensioning nga, nauuna yung hardening ng concrete before pre-stressing. Dito natin makikita na yung idealized na itsura ng ating strand is naka-center siya. Pero actually, yung nangyayari sa kanya, in reality, nakababa siya dito sa portion ng duct natin, no? Na since meron siyang contact dun sa surface ng duct natin, ibig sabihin meron siyang friction once na nahihigit na yung o na i-stress na yung bakal natin. So, nagkakameron siya ng friction dun sa ating duct, no? Dun sa surface ng duct, ano yung surface ng mismong tendon natin. Okay? And in calculating losses due to friction, we have two dependent variables. O dito nakadepend yung value ng friction loss natin. We have yung tinatawag nating curvature effect o yung friction due to curvature. And then we have wobble effects o yung friction due to wobble. No? So, ayan, so curvature effects is a function of the tendon form or alignment. So basta may curvature yung ating tendon, i-exist tong effect na to. And then si wobble effect, basta straight yung tendon natin. Okay? Nag-exist siya. So, ibig sabihin kung kung naka-curve o parabolic yung tendon natin, nag-exist sa kanya are both curvature and wobble. And then kapag straight yung tendon natin, si wobble yan yung nag-exist sa kanya and wala sa curvature, no? And ayan, kailangan natin siya munang i-treat separately or i-analyze separately yung dalawa. Okay? So the maximum frictional stress loss occurs at the far end of the beam if jacking is from one end. So, diba yung one end natin, tinatawag nating live end daw yun, kung saan nandun yung jacking equipment natin. So dito nangyayari yung pre-stress ng tendon natin. And then at the end of that, nandun yung ating dead end na tinatawag o yung ating naka-fix na position ng ating tendon wherein yung habang ni-stress natin siya, again, nagkakameron ng friction between the strand and the duct inside. No? Kaya nagkakameron tayo ng losses due to friction. Okay? So, in curvature effects, as the tendon is pulled with a force of F1 at the jacking end, it will encounter friction with the surrounding duct or sheet, no? Such as the stress in the tendon will vary from the jacking plane to a distance L along the span. So, magbabari yung value niya syempre, no? Kasi dito sa may jacking end natin, mas mabilis yung pulling ng tendon kasi nandun yung jacking force natin na habang lumalayo tayo doon, makikita natin na dito yung losses natin, yung friction losses, yung friction value natin is mas maliit na siya, no? Kaya kung makikita nyo dito sa graph natin, dito sa end o yung distance along the tendon, makikita natin mas sudden yung decrease in jacking stress or jacking force natin. Kasi nga, nandun mismo yung malaking friction, no? Doon sa area na to. And then pag nakita natin, at some distance, no, L, kumbaga umuunti na yung nababawas na friction, eventually parang babalik na siya doon sa original value niya. Okay? So, iyan yung nangyayari kapag sa curvature effect natin. And then since curvature yan, so kailangan pakita natin kung paano makukuha yung formula sa kanya. Okay? And makukuha yung formula sa kanya by considering a infinitesimal length of the tendon. Okay? So, halimbawa, ito yung infinitesimal length natin. And then isolate natin. Then, if yung mu natin denotes yung coefficient of friction between the tendon and the duct due to the curvature effect, the resulting formula is itong ika-calculate natin. So dito, tingnan muna natin dito sa representative na ano natin ng tendon, no? So ito di ba in-assume natin na naka-curve yan. So makikita natin to, meron siyang radius, no, from a circle. Okay? So parang dito, para makuha natin yung length niya, kailangan natin to consider a sector ng circle, no? So para makuha to, ano bang formula ng sector ng circle, yung length ng sector? Diba? S is equals to radius times yung theta natin. Let's say yung angle na kino-consider natin is a maliit, no? Change alpha. Okay? So, dito para makuha natin si length na to, i-designate ko lang to as length. Tawagin natin tong dx, no? Kasi strip lang yan. So, dx is equals sa r times d alpha. So, yan yung formula natin for sector, di ba? And then, para makuha natin si angle alpha, we can have dx over r. Okay? So, kung hindi representative yung pinag-uusapan natin, this can mean na si alpha, pwede natin makuha as yung length natin na kino-consider for the curvature effect over yung R natin. Okay? So yan daw yung alpha natin pag kino-consider natin. Okay? Then since friction yung pinag-uusapan natin, lagi yan opposing dun sa ating movement o dun sa force natin. Dito ang force natin si F1. Kaya makikita natin yung friction natin dito is yung direction niya is opposing ng direction ni F1. Dito kasi nai-stress, di ba? So yung friction natin is opposed ng direction na yon. Kaya pag kinuha natin yung force na dito sa other end, it will be the net nung F1 natin o nung pre-stressing force natin doon minus yung friction natin. Okay? And paano ba natin makukuha si value ni friction? Okay? So, makikita natin dito si ano bang formula ni friction? Okay? Kung mabalikan natin, si friction, let's say, tawagin natin FF na lang para sa friction. Para makuha natin yung kanyang value, kailangan natin yung formula ni device, mu times n. Okay? Mu n. Okay? Normal force. Kailangan natin ng normal force. And lalagyan ko lang to ng negative sign kasi nga opposing siya ng direction natin. No? Pero wala pa tayong value ni normal force. And saan manggagaling si normal force? Manggagaling siya dito sa analysis natin dito. Si normal force is naka perpendicular doon sa force natin. So kung babalik tayo sa tandaan niyo yung simple curve sa sa tawag nito sa surveying. Okay? So let's say meron tayong ito, ganito. Okay? So halimbawa, ito yung simple curve natin. Ibahin ko yung kulay. Okay? So, halimbawa yan yung simple curve natin. Tapos, i-assume ko na itong portion na to, ito yung force F1 natin. Move ko lang ng konti. Okay? And then, ito yung force 2 natin. Okay? Diba, itong angle na to is, sabi natin, it is the same value nung ating central angle, no? Or yung alpha natin. Okay? And si normal force is perpendicular dun sa ating frictional force, no? So, assume natin na ito yung ating normal force. Okay? Ayan. Yan si normal force natin. Itong curvature na to, ito yung strip ng ating tendon, no? Ito yan. Okay? So, inano ko lang, nirotate ko lang yung representation niya. And then, kung 90 degrees yan, okay, pwede kong i-connect si F2 dito sa kabilang side, no? Okay, ito. Si F2. And then, itong angle na to will be the same as alpha. Okay? So, pwede natin makuha si N using yung right triangle na to. Okay? May right triangle tayo. So, may right triangle tayong ganyan para makuha si normal force in terms ni F1 kasi yun yung may value tayo sa una eh. Gagawin natin is tangent of alpha is equals to n over F1 or n natin is equals to F1 tangent alpha. Okay? Pero since yung ating consideration kapag mga gantong curvature is very small lang talaga yung angle natin. So according to small angle concept, no, or theorem, ang tangent alpha natin can be almost equal to alpha din. Okay? So ibig sabihin yung normal force natin can be equals to F1 alpha na lang. Okay? Yeah. So ito yung ating normal force. Okay? So gawin ko lang tong para consistent tayo, gawin ko lang tong d alpha, no? Para magamit natin doon sa formula mamaya. Okay, so d alpha. Okay? So, ayan, may value na tayo ng normal force. So, pwede natin siya i-substitute dito. Negative mu d alpha. Okay? So, yan daw yung value natin. And when we try to integrate, kasi di ba differential equation to. So, dff, negative mu d alpha, kung i-try natin siyang wait lang, nawala yung F1, ano? Should be F1 d alpha. Okay? F1 d alpha. So pwede natin ilagay si F dito, no? Si F1. Okay? So, ayan. And then when we try to integrate, ang kukunin natin ito is from F1 to F2. Okay? So, ang integration nito is ln F, F1, F2 is equals to mu alpha. Okay? Then pag ito, inano pa natin, kinontinue natin, L2 minus ln F1 is equals to negative mu alpha. And then ln F2 over F1 is equals to negative mu alpha. And then ang ln ay equivalent yan sa log E. Okay? So log E F2 over F1 is equals to mu alpha. Then property ng logarithm, we can create na F2 over F1 is equals to E raised to negative mu alpha. So, ang F2 natin o yung force natin na kasunod is equivalent to F1 times E raised to negative E mu alpha. Okay? And kung hanapin natin si change in our friction, yung nabawas natin, so friction loss natin ngayon due to friction is equals to yung kung ano yung ating value ng F1 minus ng F2. Okay? So, kulang to. Okay. So, this will be equals to F1 minus F1 E mu alpha. So, ating ang FPF natin is equals to, factor out natin yung F1, 1 minus E negative mu alpha. Okay? So, this will be our formula kapag curvature yung hinahanap natin for ito yung loss due to curvature effects. Okay? Na yung alpha natin is considered na ito yung formula natin for alpha. Okay? So, ayan yung value natin. So, pwede mo na lang substitute yung alpha na LR siya dito. Okay? And then, kung ito yung effect niya para dun sa curvature effect, okay? Since friction din naman si wobble effect, pwede natin substitute na lang na palitan lang natin yung kanyang value ng friction dito. Gagawin lang natin siyang negative KL. Okay? Kaya yung F2 niya equals sa F1 e raised to negative KL. Okay? Kaya yung pwede natin siyang pagsamahin ngayon. So yung pinaka-effect ngayon ng friction due to yung friction loss natin will be F1 times 1 minus mu negative E raised to negative mu alpha minus K times L. Okay? So this is our main formula now kapag consider natin siya ng complete yung formula natin. Okay? And then meron siyang simplification na pwede. Okay? Yung simplification niya is considering lang na constant yung value ng friction dun sa curvature natin. And ang mangyayari sa kanya is mula dito sa derivation natin na to. Okay? So, parang mangyayari sa kanya kapag naging constant siya, yung F2 natin para makuha siya, equal siya sa F1 minus yung friction force natin. Okay? So, pwede natin makuha si friction force as F2 minus F1. Tapos negative mu times N. And then, kukunin natin yung value ng N na calculate na natin kanina. Equal siya sa negative mu F1 times alpha natin. So, meron tayong value na F2 minus F1 all over F1 is equals to negative mu alpha. And then, kung yung total yan, kasama yung sa wobble effect, minus K times L lang tayo. Okay? And then, so, kaya makikita nyo, hindi naka-display, no? So, ito yung formula para sa simplified version, no? Ito yung simplified. Okay? So, ngayon, pag kinuha natin yung value ni F2, so ibabalik lang natin dun sa dito, no? Okay? So, this should be F2 is equals to F1 minus, this will be mu N minus mu N minus KL. Okay? So, yung F2 natin will be F1 minus mu N plus KL. Wait lang. Okay, so dito, mu N, so magiging F1 minus F1 mu alpha, and then F1 minus F1 mu alpha plus KL. Okay, kasi may negative na dun sa labas. Okay, so ito yung magiging value ni F2 ngayon. Value ni F2. So, para makuha yung ating change. Okay, yung change in FBF, that should be F2 minus F1. So, F1 minus F2 pala, sorry. From our left side, papunta sa right. So, this should be F1 minus F1 minus F1 mu alpha plus AN. So, this is F1 minus F1 plus F1 mu alpha plus AN. So, magka-cancel out to. Kaya ang formula equals to F1 mu alpha plus AL, which is the same as the one reflected dun sa slide natin kanina. Okay. So, ito yan. Kung paano nakuha itong simplified na to, dito yan ang galing, no? Sa derivation na yan. Okay? And then, para daw makuha yung alpha, we can consider this one. So, let's say meron tayong curvature. Let's say natin CM is yung ating distance from our center line and then hanggang dun sa intersection ng ating tangent line mula dun sa end of curve natin. Makukuha daw natin yung value ni alpha by using this relation, no? So, assuming na si M equals sa almost equal sa 2y. Okay? Ano ba 'yon? So, nangyari parang doon sa gitna, ito ay 2y and then ito ay x over 2. Kung gusto natin makuha si alpha, so ito is alpha over 2. Okay? So para makuha si alpha over 2, we have tangent of alpha over 2 is equals to 2y over x over 2. So this will be, since ito is nakatangent ulit ng alpha, so very small siya. So, pwede na siya maging alpha over 2 is equals to 4y over x. Kaya, pag kinross multiply natin yung 2 sa ilalim, alpha is equals to 8y over x, which is, ito yung pinanggalingan. Okay, itong figure na to. Okay? So, yan yung mga kailangan tandaan na formula para sa laws of friction. Okay? Ngayon, okay. So, dito, meron mga values ng factor K and mu na bigay sa table, pero usually dapat given siya sa problem. Okay? Kung hindi man, we can use assume values yung mu natin tsaka k to calculate para depende kung anong klase ng tendon meron tayo. Okay? So let's start with an example. Okay? And so a prestressed concrete beam is continuous over two span and its curved tendon is to be tensioned from both ends. Compute the percentage loss of prestress due to friction from one end to the center of the beam. So ibig sabihin from this point hanggang dito lang tayo sa this point na to. Okay, dito sa center natin kasi ito ay parehas naman siya ng center line natin ha. So kaya yun lang consider. The coefficient of friction between the cable and the duct is taken as 0.4 and the average wobble length effect is 0.008 per feet. Okay? So there are three methods kung paano i-solve ito. Yung first one is using yung pinaka-general estimate natin. Galing dito sa derivation natin. So itong formula na to. Okay? So ito is corresponding dun sa change in change in friction, yung ibig sabihin nitong ratio na to. Kaya pwede natin gamitin to. So, try natin yun dito. So, yung first one, we have F2 minus F1 over F1 is equals to negative mu alpha minus KL. Okay? We need to identify muna yung mga values natin. Si mu, given naman si mu, ito si mu. Okay? Si K given. Ang wala natin ay si alpha. No? So si alpha natin, from here, kailangan natin, di ba, from previous, kailangan niya is, formula natin is, saan na yan? L over R. Okay? Pero kung titingnan nyo dito sa given natin, sa figure natin, ito yung alpha na yon, kung dalawang to. Okay? So, ibig sabihin, pwede nating pagsamahin na lang tong dalawang to as estimation. Okay. Para dun sa alpha natin. And then yung length natin is from point A hanggang point E. Okay. So kung ano yung length na yun. Okay. So we have mu is equals to 0.4 times yung alpha natin na 0.167 plus 0.1 minus 0.008 times yung length natin, that is 17.5 plus 12.5 plus 12.5 plus 17.5 plus 10. That is equals to 70 feet. Okay? Calculate yan. 0.4 times 0.167 times 0.1 minus 0.008 times 70. So we will have 0.0008 times 70, 0.167 plus 0.1. We have a value of negative 0.1628 or 16.28% na loss due to friction. Okay? Pero madaming hindi kinonsider dyan. So itong value na to, usually is hindi siya ginagamit talaga kasi hindi niya na-consider yung effect ng friction o yung change ng friction all throughout dun sa system natin. Okay? So, ito yung sa unang method na pwedeng value niya. Next, we can use yung simplified approach natin na ang formula is, saan yung formula natin? Ito yung formula ang gagamitin natin, no? Yung value ng F2. Okay, ito. Okay? So by segment yung analysis niyan, ibig sabihin. So using simplified formula. Okay? So ang general formula F2 is equals to F1 minus F1 times mu alpha plus Kn. And then by segment tayo. Segment A, B muna tayo from A to B. Okay? So, ang F2 natin dyan, ibig sabihin is kung ano yung friction niya at B. Okay? So ito ay FA minus FA. Pwede natin factor out na pala yung F1, no? Gawin na natin FA times 1 minus mu alpha plus K alpha. Okay? So ano yung magiging value ngayon ni FA? So sa FA, hindi natin alam. Walang given na jacking force. So in terms ni FA yung consideration natin. So dito, makikita ninyo, yung A to B natin is a straight line, no? Wala siyang curvature. Yung curvature niya mag-start pa dito sa point na to kung saan nandun yung radius natin. So ito pa yung curve natin. So ito is straight lang. So ibig sabihin, si curvature effect, hindi siya nag-exist dun sa first segment natin. So this one will be equal to 0. Okay? So FA times 1 minus, yung K natin dyan will be 0.0008 times yung length ng segment na yun, which is 17.5. Okay? So FB natin will be equals to 1 minus 0.0008 times 17.5. We have a value of 0.986 ng FA. Okay? So, ibig sabihin nun, from this point, okay, due to wobble effect, pagpunta nyo sa B, yung pre-stressing natin is 0.986 na lang nung original pre-stressing natin nung nag-start tayo. Okay? So, yun yung segment A, B. Okay? Next, segment BC tayo. Okay ko lang to. Okay, so ito yung diagram natin. So segment B to C. Okay. So again, formula natin is F2 is equals to F1 times 1 minus mu alpha plus KL. Okay. So dito ang F2 natin ngayon will be yung value natin, yung end natin. So FC yun will be FB times 1 minus, since ito is a curve, meron tayong curvature effect. So hindi yan 0. Then meron tayong wobble effect. Okay? So ano yung mu natin? So mu is 0.4 kanina doon sa problem, which is stated naman, no? 0.4. And then ano yung alpha natin? Alpha natin is ito, no? Itong alpha na yan, do sa, again, kung babalikan natin yung ating sa simple curves, ito ay equals dun sa alpha natin. So we have 0.4 times 0.167. Okay? Plus K natin, 0.008 times yung length natin. So ang length ng B, punta kay C is 25. So 25. Okay? Substitute natin yung value ni FB. Si FB as calculated natin is 0.986 ng FA. So 0.986 ng FA times, kung ano man yung mag-answer nito, 0.4 times 0.167 plus 0.008 times 25. Then 1 minus that answer, we have 0.9132. And then FC natin, multiply lang natin yung dalawa, will be equals to 0.900 FA. Okay? So ito yung para sa segment BC. So continuing with the next segment. So segment CD. Okay? So makikita natin dito, segment CD is a straight, no? Wala siyang curvature, hindi siya nagka-curve. So sabihin FD is equals to FC times 1 minus yung ating curvature effect will be 0 plus 0.008 times yung length niya, which is from C to D 17.5. Okay. So 17.5. So FC natin is 0.900 FA multiplied by 0.008 times 17.5. Then 1 minus that answer, that is 0.986. So FD natin times 0.9, that is 0.8874 ng FA. Then last segment D to E. Okay. So FE is equals to FD. 1 minus, so dito, yung D to E natin, okay, itong D to E natin is half nitong curvature na to, no? Itong curvature na to. So, kailangan natin ng curvature effect. So, 0.4. Tapos times yung alpha natin, given dito, alpha niya is 0.1. So, 0.1 plus 0.00008 times yung value ng length natin, which is 10. So, equals to 0.8874 FA multiplied by 0.4 times 0.1 plus 0.08 times 10 plus 1 minus that answer. So, 0.952. So, FE natin, sa pinaka-end ng segment na kinoconsider natin is how much na lang ang FE natin? 0.845 FE natin. So, kung yung ating total pre-stressing loss due to friction, that will be from FA minus yung ating 0.845 na FA, okay, over yung FA natin. So ito yung formula kanina, no? Ito yung formula kanina na F2 minus F1 over F. Hindi, baliktad. Yung F1 minus F2 over F1. Okay? So this is, or kahit hindi na natin lagay ng FA sa ilalim, no? So 1 minus 0.845, meaning nag-loss siya ng 0.155 or 15.5%. Okay? Na, yun yung difference na doon sa una, no? 16.28 yung una, then ito is 15.5%. Okay? Ito yung sa simplified approach. Then meron pa tayong isa, which is yung accurate approach, no? Yung ating third method. Na yung formula niya is naiba lang pero yung segmenting parehas, no? Try natin yung letter C. So sa C, so sa method C, so ang value ng F2 natin ay equal sa F1 E raised to mu alpha plus K alpha, KL. Okay? So ito yung kaninang na-derive natin mula dun sa derivation natin dito. Okay, dito sa portion na to, which is yung value ng F2. Okay? So ito yun, no? Okay? So segment by segment ulit. Segment A to B. So FB is equals to FA. E negative. Mu natin dito will be 0 plus 0.008 times yung 17.5 natin. FB is equals to E raised to negative 0.0008 times 17.5. That is equivalent to 0.986 FA. Okay. Segment PC. Kaya kung ganito yung solution, pwede kayo magawa ng table, no? Para mas mabilis. FBE. So, dito may curvature tayo. So, 0.4 times yung value ng ating alpha, which is 0.167, 0.008 times 20. FC is equals to 0.986 FA times E raised to negative 0.4, 0.167 plus 0.008 times 25. So we have a value of 0.917. So multiply dun sa 0.986, we have 0.904 FA. And segment CD. So FD is equals to FC. E negative 0 plus 0.008 multiplied by yung length niya, which is 17.5. 0.904 FA multiplied by E raised to negative 0.008, 17.5, that is 0.9861. So times 0.904, so 0.891 FA, yan yung FD natin. Then last segment DE, we have FE is equals to FDE negative. So 0.4 times yung alpha natin is 0.1 plus 0.008 times yung length natin, which is 10. So 0.891 FA multiplied by E raised to negative 0.4. 0.4 times 0.1 plus 0.008 times 10, we have 0.953. So yung FE natin is equals to 0.849 FA. Okay. So yung ating change in prestress due to friction will be equals to FA. Yung kahit yung coefficient na lang lagay natin, 1 minus yung 0.849 na nakuha natin. So yung ating change in friction loss will be 1 minus 0.849. That is 0.151 or 15.1%. Okay. So yan yung loss natin. Okay. Makikita natin medyo konti lang yung discrepancy niya doon sa simplified. Okay? Pero makita nyo doon sa accurate procedure, sabihin, konti lang yung nababawas sa pre-stressing natin. Okay? So, any solution doon sa tatlo, kung mapapalabas nyo sa multiple choice, yung sagot, no? Pwede nyo i-consider. Pero, if you want to have a more desirable answer, doon tayo sa accurate solution, which is yung sa letter C. Okay? So ito yung sa loss due to friction. Before we proceed, do you have any question for this part? Hello? Okay. Okay, I hope you can review this, no? Okay, next, we have, this is another one. Okay, another example pala. So assume that the alignment characteristic of the tendon in the post-tension beam shown If the tendon is made of 7-wire uncoated strands and flexible metal sheeting, compute the frictional loss of stress in the pre-stressing wires due to the curvature of the wobble effects. Okay? So, walang given ng mu, tsaka value ng K, no? Pero binigay ko anong type ng steel, no? So, we have 7-wire uncoated strand in flexible metal sheeting. Okay? So, tingnan natin yung table kanina. Okay? So, flexible na 7-wire in ito. So, dito tayo ibig sabihin pipili. Okay? So, it's in a range. Okay? So, I think mas maganda kung average na lang yung kukunin natin, no? So, yung average ng 0.0020 plus 0.005 is equal sa 0.00125 para sa K. 125. Okay? And then dito, 0.15 plus 0.25 and 2 is 0.2. Okay? So, yun na lang yung gamitin natin dito sa example natin. So, 0.00125 and 0.2. Okay? Pinapahanap is yung frictional loss. So, by formula, yung simplified natin kanina, so we have F2 minus F1 is equals to F1 equals to negative mu alpha minus K times L. So, wala tayong value ng alpha, pero pwede natin gamitin yung formula na 8y over x sa calculation natin. So, yung y natin is yung horizontal distance o yung vertical distance from the center, yung pinaka maximum na downward distance natin, yung E. Okay? So, 8 times 11 all over yung x natin is i-consider natin ay 25, no? Kasi 25 is naka-fit yan. So, kailangan times natin ito para maging inches. Okay? So, yung alpha natin in radians is 8 times 11 times 25 over 12. Okay? Pero kung effect ng nung wobble effect dun sa buong curvature, gawin nating full yung length natin. Okay? Gawin natin 50 to. Okay? Para whole length nung natin, curvature natin. So we have 0.147 as our value ng alpha. So dito, we have negative 0.2 times 0.147 minus yung K natin is 0.00125. Then ang length natin is 50. So, 0.2 times 0.147 minus 0.00125 times 50. So we have a value of 0.0125 ba? Sobra na isang 0, no? Zero zero one two five. Answer of 0.0919 times yun ng 100, 9.19% na loss. Okay? May value pala tayo ng F1, no? Ito. Okay, so, wait lang. Multiply natin yan. So, ito is F2 minus F1. Ito di ba yung change, ibig sabihin. So, F1 times yung value na makukuha natin dito. So, ang F natin dito is itong pre-stressing natin na ito, 309. So, 309,825 pounds multiplied by, okay, kung ano yung value nun. Value na kuha is 0.919. So, this is 309,825 times 0.0919. Our answer is 28,472.9175 pounds. Ito yung ating due to pre-stressing loss. Okay? Question dito sa number 2, example for friction loss. Okay? Next, we have yung anchorage seating loss. So, si anchorage seating loss losses occur in post-tension members due to the seating of wedges in the anchors. No? So, when the jacking force is transferred to the anchorage, so they can also occur in pre-stressing casting beds of precession members due to the adjustment expected when the pre-stressing force is transferred to their beds. Okay? So, pero mas madali yung formula for anchorage seating loss since this is based from the change in doon sa strain ng nung pre-stressing natin. Pag nakuha natin yung strain, multiply lang natin dun sa value ng modulus of elasticity ng tendon natin, we will have yung ating loss due to anchorage slip. Okay? So the magnitude of the overstressing that is necessary depends on the anchorage system. So dapat ang nagbibigay ng value ng data dun sa uh, kayang i-carry na deformation ng tendon is dapat si manufacturer yung magbibigay ng data na yan. Okay? So makita natin dito right after jacking, okay? A sudden decrease ulit ng value ng pre-stressing force na at some time hanggang mag-set siya, continuous yung increase ng pagbawas niya. Okay? Then eventually mag-intersect na siya dito once na tapos na mag-adjust yung strand natin upon dun sa pag-release niya sa anchorage natin. Okay? So the percentage of loss due to anchorage slip become very high in short beam elements and thus becomes of major significance in short span beams kasi magiging yung divisor natin dito will be a small number. So definitely yung strain natin will be a larger number. So yung loss natin will be a larger value. Kaya mas lalaki yung value ng loss natin. Okay? So let's have an example. So dito nakalagay, compute the anchorage seating loss of the estimated slip in post-tension beam spanning 15 meters is 6.35 mm. The modulus of elasticity of the tendons is given as 190 gigapascal. Okay? Compute the anchorage seating loss. Okay? So dito may given tayong deformation. Okay, ito, yung delta natin. And then we have a length. Okay? So, pag kinuha natin yung deformation natin due to anchorage slip equals yun sa yung strain natin due to anchorage slip rather. So, strain natin due to anchorage slip equals yun sa delta over original length. So, 6.35 mm divided by yung length natin, 15 meters, so times 10 to the 3 mm. Since strain yan, dapat wala tayong unit. So divide 15,000, that is 4.23 times 10 to the negative 4. So, makuha natin yung value ng loss, okay, using EA times yung value ng modulus of elasticity ng pre-stressing strand na given na 190 GPa. So, this is 4.23 times 10 to the negative 4 times 190. So, 190 times 10 to the 3 MPa. Okay. So, yung ating frictional loss, so yung ating pre-stressing loss due to anchorage leak will be 4.23 times 10 to the negative 4 times 190 times 10 to the 3. Okay. So, we have 80.37 MPa. So, ito yung mababawas na value dun sa ating anchorage kapag natin siya. So, basically, substitution lang siya ng formula halos dun sa given natin. Right after ma-identify natin yung strain, multiply lang natin dun sa natin. Okay? So, kung papansinin nyo, ito yung Hooke's law natin for stress and strain, no? Kung matatandaan ninyo. So, ginamit lang yan dyan. Okay? So, that's for anchorage slip. Then for our change of pre-stress due to bending of a member, o yung B. So as the member bends due to pre-stress or external load, it becomes convex or concave depending on the nature of the load. So we have itong naka-convex tayo, and then we have concave. Okay? So the change in pre-stress and steel can be calculated also using yung Hooke's law natin. So ibig sabihin yung strain in concrete, tapos i-multiply lang natin sa value nung ating modulus of elasticity nung ating pre-stressing strand. Okay? So, ibig sabihin, paano natin makukuha yung strain ng concrete? So, sa strain ng concrete is manggagaling dun sa bending force natin. So, kailangan kukunin natin muna para makuha natin si strain ng concrete, kailangan kunin natin si stress ng concrete over yung modulus of elasticity natin ng concrete. Okay? And si stress, makukuha natin yan kung bending pinag-uusapan natin using MC over I. Okay? So, pag nakuha natin MC over I, substitute nyo lang dito, and then substitute, makukuha natin to, and then tsaka mo siyang multiply dito. Okay? So, parang lang kayo nag-strength of materials dito. So, let's have this example. A simply supported concrete beam, 200 mm by 450 mm deep, is pre-stressed with an unbonded tendon to the lower thirds with a total initial pre-stress of 650 kN. Compute the loss of pre-stress in the tendon due to bowing up of the beam under pre-stress, neglecting the weight of the beam itself. If we have modulus of elasticity of the tendon and concrete are 200 MPa and 28,000 MPa respectively. Okay? So, meron daw tayong concrete beam. So 200 by 450 mm. Okay? And then, meron siyang unbonded tendon dun sa lower third point. Okay? So, sabihin, divide mo ng 3 yung 450. Okay, so this is 150. Okay? So, mula dun sa ating center line, ano yung distance nito? Okay? So, 450, divide mo ng 2, minus 150, that is 75. So, ito yung ating eccentricity. Okay? And then we have an initial pre-stress by given equals to 650 kilonewton. Okay? Neglecting yung weight ng beam, kailangan natin ng modulus of nung loss natin. Okay? So, loss natin due to bending is equals to strain in concrete times yung ating modulus of elasticity ng pre-stressing strand. Okay? So, strain ni concrete, manggagaling siya sa stress ni concrete over sa modulus of elasticity ni concrete. Okay? And then for normal weight concrete, okay, according to NSCP, ang modulus of elasticity natin, given naman pala. Okay? Kung halimbawa hindi given, ang value niya is 4,700 times square root of F prime C. Okay? Pag normal weight siya. Pag lightweight, may ibang formula yan. So, kunin natin yung stress. So, yung stress natin will be due dun sa moment natin ng member. So yung moment na yun magagaling sa pre-stressing natin kasi meron tayong pre-stressing strand. So, ibig sabihin, kung yung dun sa beam natin dati, okay, bawa ito yung beam natin, yung ating pre-stressing. So, dito yung ating PI, and then dito ta-transfer yung ating P, and then magkakos siya ng rotation na pag ganito. Okay? So, yung moment na yan equals yan dun sa P times E natin. Okay? So, ito will be P times E. P times E. So, ito yung ating moment times yung ang kailangan natin is yung E natin dun sa steel. So, ilang din to over yung I natin o inertia natin. So, substitute lang natin. You have 650 times 10 to the 3 times E natin is 75 squared. Yung inertia natin, walang nakalagay. So, that is a square. So, 200 times 450 cube. Tapos, over 12 yun. So, kaya lalagay ko na lang sa taas. Okay? May makukuha tayong stress ng concrete. Will be 650 times 375 squared times 12 all over 200 times 400 cube. We have a stress of 3.428 MPa. Okay? Paras din yan ng FC ha. Baka malito ko ba't naging nagka-sigma, no? Paras lang yan ng FC. Okay? So ngayon meron tayong stress. So lagay ko rin dito para pwede na natin substitute yun doon. Okay? So yung strain natin ng concrete will be FC over AC. So this is 3.428 MPa divided by yung ating concrete is 28 MPa. 28,000 MPa. So strain natin in concrete will be equals to 1.224 times 10 to the negative 4. And then, kunin natin yung change in bending is equals to E, C, plus yung sa steel natin. So that is 1.224 times 10 to the negative 4 times yung ating 200 times 10 to the 3 MPa. So yung ating loss due to bending will be equals to 24.484 MPa. So this will be our answer. Dito. Okay? Question dito sa bending. So may note siya dito, no? Dito, any loss due to bending need not be taken into consideration if the pre-stressing stress level is measured after the beam has already bent. Okay? Which is yun yung usual case natin. So, unless otherwise noted na meron siyang loss due to bending, tsaka lang natin siya i-calculate. Pero kung wala siyang sinabi, pwede natin i-disregard si bending dun sa consideration ng mga losses natin. Okay? So, before we proceed, question? Okay. Okay. So now, punta tayo sa example na isosolve natin lahat ng mga losses natin sa given problem. Okay? So, ayan. So, this is also reflected kay Nawi na book, no? So, if ever hindi nyo masyado maintindihan yung discussion ngayon, you can refer dun sa kay Nawi na example. Pero, I doubt na baka mas mahirapan kayo maintindihan kasi ako nahirapan ako intindihan yung example niya. Kaya yung solution na gagawin ko will be different from the solution na reflected talaga dun sa book ni Nawi, okay, for this example. Okay, pero kinuha ko yung numerical example niya to show you how to solve it na hindi na madaming sinasabi pa. Okay. Okay, so let's have this one. So, is simply supported pretension. Okay, so sa ganitong problem, ang first na gagawin nyo is identify nyo yung mga key terms na kailangan natin tandaan para kasi 'di ba may mga dependent tayong value. Depende sa system, depende sa type of strand, okay? Kung stress relief or low relaxation siya. And then meron din tayo kung steam cured or moist cured yung concrete. Then we also have other parameters pa kaya kailangan yun yung ite-take note natin sa mga gantong problem, okay? So meron tayong simply supported na pretension, okay? Pretension yung system natin. And then yung concrete natin is lightweight. Steam cured steam cured tayo. So babalikan natin yung formula mamaya nung para sa may steam cured, no? Double T beam as shown is pre-stressed by 12 1-inch diameter 270K grade. Stress relief siya. Okay? The strands are harp and the eccentricity at midspan is taken as 8.73 inches and at the end 12.98 inch. Compute the pre-stress loss at the critical section in the beam. Due to dead load and superimposed dead load, assume natin daw na ang critical section natin is at 0.4 nung span natin. Considering that it can sometimes govern in cases of moving loads and also in continuous spans. Okay? So, yung mga ika-calculate daw nating loading stages are stage 1, ibig sabihin at transfer. We have stage 2, after yung concrete topping natin is placed. Okay? And then, stage 3 or last stage, 2 years after yung concrete topping is placed. Ba't nagkameron ng concrete topping? Nakalagay dito na, suppose that the topping is 2 inches, normal weight. So dito normal weight naman yung pinatong, no? Kanina lightweight siya, tapos yung ipinatong sa kanya, normal weight concrete. At 30 days, no? So after 30 days, matapos ikasa yung pre-stress member natin, naglagay ng normal weight concrete, yung para sa slab yan, no? Ah, para yung mga awang sa bawat bridge is mawala ng awang, kaya nalagay ng slab agad. And then suppose also that the pre-stress transfer occurred 18 hours, ayan, 18 hours after tensioning of the strands, okay? So we have given F prime C natin 5,000 PSI. So ito yung design strength natin. And then initially 3,500 PSI yung strength niya nung ibig sabihin nung mag-jack tayo ng force. May 3.5 na siya, okay? And then the following non-composite properties are as follows. We have yung area ng concrete na 615. We have inertia. And then ito is mga fiber stresses natin, fiber distances sa bottom and top. And then we have section modulus for bottom and top. Then we also have yung weight natin kapag wala siyang topping. Ibig sabihin self-weight natin kapag wala pa siyang superimposed dead load. And then yung weight ng superimposed dead load daw natin is ito, given siya. Okay? And then we have W1. So ito is I think yung moving load niya. So hindi naman natin gagamitin yan. And then FPU. So yung mga properties ng ating strand, okay? Then EPS, yeah. So assume that the post-tensioning is applied 18 hours after concrete coring. So after 18 hours na mag-cure yung concrete, meron na siyang strength na 3,500. So yun yung ibig sabihin, no? So babalikan natin ngayon is yung ating table kanina, yung pina-recall natin. Okay, dito. Okay? So tayo ay pre-tension members, okay? So, ibig sabihin, ito lang yung mga losses natin. And sa stage 1 natin, si stage 1 is at transfer tayo. So, ibig sabihin, at transfer, meron tayo, ayan, nakalagay. So, meron tayong elastic shortening na i-calculate. Isa sa letter A natin. Next is ito, before transfer, no? So, may relaxation tayo nun. Okay? Pero kung sa creep and shrinkage, wala tayo i-calculate sa kanya. Okay? Ibig sabihin sa stage 1, itong dalawa lang yung gagamitin natin o kukunin natin na value ng stress loss. Okay? And then si friction and anchorage, wala siya kasi pre-tension member tayo. Okay? And si bending, hindi din siya sinama kasi hindi siya na-require dun sa problem. Okay? So let's proceed dun sa pag-solve ng ating condition 1 which is at transfer. Okay? So lagay ko na lang dito. Letter A tayo. At transfer. Stage 1 natin. Okay? So, yung magiging total loss natin will be based lang sa, again, elastic shortening plus yung sa ating relaxation. Okay? So, let me open lang yung slide natin last time. Let me check. No? Ayan. So, ito yung slide natin last time. So, sa elastic shortening, meron tayo ditong formula for elastic shortening. Ay, yan, hindi ito. Hindi yan. Yan, ito. No? So, sa elastic shortening, sorry. Slideshow from current slide. Okay. Ayan. So, ito yung sa elastic shortening natin. And for pretension, ang ating formula for pre-stress, kapag ang ating tendons is may eccentricity, is kukunin natin yung kanyang stress due to pre-stressing tsaka yung self-weight niya. Tapos, ang formula natin for stress in for loss in elastic shortening is N times FCS lang. Okay? So, yun yung gagawin natin muna. Okay? So, going back to sa figure natin as sa nating presentation. Okay? So, elastic shortening muna tayo. So, kay elastic shortening, okay. So, ES. Okay? So, kailangan natin FP, ES is equals to NFCS. So, kailangan natin si N, kailangan natin si FCS. Pero ano ba yung sabi sa problem? Meron siyang critical section na binanggit. Okay? So, sabi niya, ang critical section daw natin, so ito yung gamitin natin, 0.4 siya nung span natin. So, kailangan kunin natin yun dito. No? So, kunin ko lang muna to. 0.4 nung length natin. So, kaya kunin natin yung condition muna o yung value ng eccentricity dun sa area na yun. Okay? So 0.4 ng L. So, yung 0.4 L natin, that is 0.4 times 70, yung total length natin. So, 0.4 times 70, so 28 feet. Okay? So, ibig sabihin, somewhere dito yon. Okay? Ito yung ating section na kailangan gawin. Okay? So, dito, dapat malaman natin yung distance ng eccentricity niya dun sa point na yun. Okay? Alam na natin na yung x niya o yung value niyan dito is 28 feet. ating critical section. So doon natin kukunin yung eccentricity natin. Okay, kasi gagamitin natin para sa pag-compute ng FCS. Paano natin makukuha 'yon? Pwede natin makuha using ratio and proportion ng triangle, no? So dito, may mapo-form tayong triangle dito. Okay? So, yung triangle na 'yon, okay. So yung height nito is yung eccentricity natin, so 18.73 minus yung 12.98. And then yung distance nito is 28. Yung half natin, so 35 yung half. So ito yung y natin, kailangan natin ng x. So kailangan natin ay si y. So y over x is equals to 18.73 minus 12.98. So ibig sabihin para makuha ko tong height na to, no? Kaya pinag-minus ko tong nasa gitna niya minus itong nasa tabi. Okay? Para makuha tong height ng triangle dito. Over 35 yung total length natin. Since alam natin yung value ng x, so 18.73 minus 12.98, that is 5.75 over 35. Tapos yung x natin is nakalculate natin na 28. So makukuha natin yung height dun sa portion na yun, which is 35. So 4.6. Pero yung 4.6 na yun is ito palang portion na to. Okay, ito pa lang yun. Itong portion na to. Okay. So kailangan add tayo ulit ng, lagay ko na lang EC. So para doon sa critical section. So yung 12.98 na distance plus yung calculated na y natin. So 12.98 plus 4.6. We have eccentricity dun sa critical section as 17.58 inch. Okay? So yan. So may value na tayo ni E. Next, so kung calculate natin yung FCS niya, okay? So si FCS niya is due to distressing natin. Okay? So negative P over A yan. Lalagyan ko lang ng section, no? So limbawa ito yung ating section. Ayan. So yung ating pre-stressing is meron tayong negative P over A. And then, itong force na to, pag nag-rotate siya along do sa neutral axis natin, iikot siya ng paganyan. Okay? So, paganto yan. Okay? So, pag paganyan yung beam natin, so, bawa mag-deflect siya ng paganyan, sabihin yung beam natin mag-iitsurang ganyan. Okay? So, ibig sabihin yung stress natin is compression yung ilalim, tension yung taas. So, compression, yung ilalim, tension yung taas. Compression, tension. Okay? So, negative PE, ito yung moment natin due dun sa eccentricity times yung eccentricity over inertia. Okay? Then, meron tayong load or dito. No? Yung load natin na yan is magkakos siya ng bending na positive. Okay? So, compressive to, then tensile tong ilalim. So, dito will be compressive yung taas, tensile yung baba. Okay? So, that is yung moment ng self-weight natin times E all over I. Okay? So, yan yung formula natin for FCS. FCS natin will now be negative P over A minus P E squared over I plus M E over I. Okay? Ngayon, calculate natin yung mga value. Wala pa tayong value ng moment. And ang moment natin is at that point, no? So para makuha yung moment, kailangan mag-cut tayo ng section. Babalik ka dun sa Uh, yes, naka-fit yung length natin at x, no? Naka-fit tayo. Okay. So dito nag-cancel naman yung fit, no? Kaya hindi ko na nilagay. Ito naka-fit, kaya nag-cancel out to. Kaya natira inches dito. Okay. So, again, paano natin kukunin yung moment? So, kailangan magka tayo ng section, no? Paano tayo humahanap ng moment? Using shear and moment function. Okay? So, kung simply supported yung beam natin, so babalik tayo sa theory, no? So, simply supported yung beam natin, okay? And then meron tayong distributed load sa kanya, okay, na W. Okay, meron siyang length na L. Kung gusto natin kunin yung reaction dito, paano natin makukuha yung reaction? So, di ba ito is meron siyang uh, equivalent concentrated load na WL. Okay? So, ibig sabihin yung reaction natin, since yun ang loading, mag-sharing sila ng 12 WL over 2 tsaka WL over 2. Okay? And then, paano kung halimbawa, kailangan natin ng moment at a certain distance? Yung distance natin na yun yung 28 natin. No? Lagi kong X. Paano natin makukuha yung moment niya? So, kailangan mag-cut tayo ng section. Ayan, ito yung cut section natin. Ito yung ating weight. Tawagin ko ulit W. Then meron tayong support na WL over 2 ang reaction. Okay? Then ito may distance tayong X mula doon sa cut section natin. Then dito, once na nagkaka tayo ng section, nag-expose siya ng internal forces. Internal forces natin are yung shear natin na V, magte-tend na mag-rotate pa clockwise. And then meron tayong moment na magte-tend na i-lift pataas yung beam natin. So ibig sabihin, i-lift siyang pa ganun. No? So laging ganun yung direction nun. Moment. So kailangan natin, pag moment dito at O. So ano ngayon yung ating ACL? So dito is WX. Okay? Kapag kinuha natin yung moment, summation of moment at point O is equals to 0. Taking counterclockwise as positive, we have moment plus ano pa mag-rotate ng counterclockwise doon. So si moment, kaya mag-moment doon. Si WX, mag-moment din doon, counterclockwise din. Itong reaction natin, mag-moment doon, clockwise direction. So plus WX times X over 2 minus WL over 2 times X is equals to 0. Kailangan natin ng value for moment. So this will be negative WX squared over 2 plus WLX over 2. Okay? So pwede kong factor out ngayon WX over 2. So this can be negative X plus L. So ito yung moment formula ng moment function natin para doon sa critical section natin. Okay? So yan yung kailangan natin value for moment. So moment natin will be equals doon sa maka-calculate natin W. So ano yung W natin? Wala pa pala tayong W. So kailangan natin ng weight ng concrete. Given ba siya? So weight niya is ito, yung 491. Pero si 491 ay anong value si 491? 491 ay yung weight ng ano kasi pound per linear feet, no? PLF. So pound per linear foot. Okay? So ibig sabihin 491 na yung W natin. So 491 pound per foot times yung X natin which is 28 foot over 2 times negative 28 feet plus 70 feet. Okay? Yung moment natin. So kung hindi nyo tanda mag-cut ng section ng ganyan, paki-review na po agad ng theory nila, no? Theory of structures. Kasi hindi laging simply supported ang condition natin. Okay? Negative 28 plus 70. So we have a value of moment na 288,708 pound foot. Okay? So meron na tayong moment. May value tayo ng P. Hindi pa given yung P, no? Okay. So yung P, may given tayo dito na FPI, no? Initially. Okay. So yung FPI daw natin, is equal to 0.7 ng FPU. And si FPU natin is equal sa 270,000. 0.7 times 270,000 PSI. So yung FPI natin will be equals to 0.7 times 270,000. That is 189,000 PSI. Nasabi natin, pwede natin i-assume na yung ating jacking force ay 10% yung mawawala, no? So pag gagawin natin itong force, gagawin natin PI. Okay? Ito yung sa jacking natin, PJ. So FPI times yung area ng prestressing steel natin. So 189,000 PSI times yung area natin, meron tayong 12 na 1/2. So 1/2 natin is 0.153. So 189 times 12 times 0.153. So meron tayong 347,004 pounds. Okay? Ito yung jacking force natin. Pero sabi natin, ang initial pre-stressing natin, dapat siya is minus 10%. So 0.9 lang nung jacking force natin. So 0.9 times 347,004 pounds. Yun yung value ng ating PI. So 312,303.6 pounds. Okay? So ito yung gagamitin natin dito sa problem na to. So dito, balikan natin, yung magiging value natin for P I is 303.6 pounds. Okay? So now we can calculate yung FCS natin. So si FCS equals to negative 312,303. Lagay ko nga ito sa taas. So dito, equate ko na lang dito. So equals negative 312,303.6 over yung area natin is given as 615, area ng concrete. Okay? So, area ng concrete. So 615 minus 312,303.6 times yung E natin, na-calculate natin ang E natin na ito. So 17.58 squared all over inertia natin from given na din, inertia, ito, 59,720. So 59,720 plus yung moment natin which is 288,708. 288,708. Pero since naka-put found yun, kailangan times natin ng 12 para maging put inch. Times 17.58 over 59,720. Okay. When calculating, FCS natin is negative 312,303.6 divide 615 minus 312,303.6 times 17.58 squared over 59,720 plus 288,708 times 12 times 17.58 divide 59,720. Our answer will be a value of negative 1,104.153. This is tayong pound inch, then ito is inch, then it's inch to the fourth, so PSI, no? pound per inch squared or PSI. Okay, so ito yung FCS natin. Kailangan natin ng N para makuha natin yung uh, FPES natin equals to N, yung FCS. So ang N natin is equals dun sa EPS over EC natin. Pero since this is initial pa lang, may formula tayo for EC. Okay? Pag tinignan natin yung NSCP, since English pala to, dapat ACI pala, no? ACI or English. Ang formula natin for EC okay, so ang unit weight ng concrete natin is equals to 33 WC raised to 1.5 square root of F prime C. So ito yung English. Okay? Sa SI or sa NSCP, ang formula niyan, EC is equals to 0.043 WC 1.5 square root of F prime C. Okay? Bakit ganyan yung gagamitin natin? Kasi lightweight yung concrete natin. Since lightweight tayo, dito tayo magde-depend. Okay? So, ayan. So kunin natin yung value. Yung value ng WC natin for lightweight, lightweight concrete, walang nakalagay. So, hindi naka-indicate, no? Pero I think, ano dito? Lightweight natin. For a while lang, no? So, sa book, nakalagay ang value ng W natin para matuloy lang natin to. Concrete ay 33 pound per foot. Okay? So, kailangan kunin natin si EC. EC is equals to 33. Hindi pala 33, no? 115. 115 times 115 raised to 1.5 square root of kung ano yung FC prime natin na initial. So, ito yung initial natin, 3,500. 3,000, 3,500. Pag kinalculate natin, that is 33 times 115 raised to 1.5 times square root of 3,500. We have a value of 2.41 times 10 to the 6 PSI. Okay? So, ang N natin will be equals to EPS is taken dun sa previous page natin, which is 28. So, this is 28 times 10 to the 6 PSI times 2.41 times 10 to the 6 PSI. Cancel yung unit. So, yung ating modular ratio, so 28,000 divide answer. Hindi, 28 to the 6. So 2.41 to the 6 is 11.62. Okay? So yung ating loss due to elastic shortening will be equals to 11.62 times yung ating 1104.153 PSI. So ating loss due to elastic shortening is equals to sa 12,830.258 PSI. So this will be our answer for elastic shortening pa lang. Um, hindi pa ito yung answer natin talaga. Elastic shortening pa lang ito. Okay? So okay na tayo dito sa elastic shortening. Question muna before proceed sa relaxation. Okay, so next, after na elastic shortening, kailangan natin ng sa relaxation naman. So, kay relaxation, kunin natin si formula ng still relaxation. Sulat ko lang muna. Okay, so mula dun sa previous discussion ulit natin, dito, relaxation, may formula tayo for relaxation na ito, no? So, pwede daw natin nangyari. Okay, so, ayan. So, yung may estimate daw natin yung prediction ng stress sa pre-stressing steel using this formula. And then, since stress relief tayo, yung K natin will be equal sa 10. Okay? And since meron tayong given na time, no? Sabi after 18 hours. Okay? So sulat ko lang muna before I go back to sa 18 hours yung ating time. And then ang formula natin for prediction ng FPSD is equals to FPI. Multiplied natin ng 1 minus log T all over K times FPI over FPY minus 0.55. Okay? So yan yung kailangan nating value. So let's go back to sa okay. So ayan yung formula lang nandoon. So we have A time na, no? And then K tayo, K is equals to 10 kasi stress relief tayo. Okay? So kailangan natin si FPI. FPI natin is yung kanina, yung 0.7 ng FPU. Tapos, i-multiply lang natin ng 0.9 kasi 90% lang ng jacking yung gagamitin natin. Okay? Kunin natin yung FPY tsaka FPU. Ang FPY natin is 0.85 ng FPU and FPU is 270,000. Okay? So, FPU is 270,000. FPY is equals 0.85 ni FPU or 0.85 ni 270,000. Okay, so this is 0.7 times 270,000 times 0.9. This is 170,000 times 100. 0.85 times 270,000. That is 229,500 PSI. Okay. Then Since wala pa naman tayo ibang duration, kasi di ba to, pwede siyang maging um, pwede siyang maging log T2 minus log T1. Pero since initial pa lang tayo at transfer stage tayo, log T2 pa lang tayo. So from 0 to 18 hours. So hindi ko na ilalagay ito, no? Log 18 hours na lang agad yung lalagay natin. So substitute natin. FPST is equals to sa value ng FPI natin, which is 170,100 multiplied by 1 minus log of 18 all over, yung K natin is 10 times FPI natin is 170, 100 all over 229, 500 minus 0.55. So, yung value natin is 170, 100 times 1 minus log of 18 all over 10 times 170 times 100 all over 229, 500 minus 0.55. You have an answer of 166,965 PSI. Okay? Ito yung FPST natin. And para makuha natin si change in FPR, so kunin lang natin is yung FPI natin minus FPST natin. Okay? So FPI natin again is 170, 100 minus 166,017.965. So ating change due to relaxation is equals to 170, 100 minus yung answer natin. That is 4,882.035 PSI. So this will be our answer for relaxation. Okay? And then para kunin yung ating total loss, no? Total loss para dun sa ating first stage equals tayo sa loss due to elastic shortening plus loss due to relaxation. That will be kopyahin natin to, 12,830 830.258 plus 4,882.035. So total loss natin is plus 12,830.258 12,830.258 plus 4,082.035. So we have a value of 16,912.293 PSI. Okay. So this will be our stage 1 loading losses. No? So this will be our answer for letter A. Minultiply ng 0.9 dito, no? Para dun sa jacking natin. Sabi natin sa previous discussion natin, minultiply ng 0.9 ito. So dito lang din 'yun. Pag itong PI natin na to, i-multiply natin ng i-divide natin dun sa area. I-try mo, no? Itong 312,303, divide mo ng 12 tsaka 0.153. 312,303.6 divided by 12 times 0.153. Ang lalabas na answer is yung 170,100. Ito. Okay? Kaya multiply ng 90. Kasi assume natin na si initial is 0.9 o 10% yung nawawala kay jacking force. Okay? Parang I've mentioned it dun sa ating um, check ko lang yung slide, no? Alam ko sinabi ko yun na 10%. Assume, pwede siyang i-assume as 10%. Parang verbally ko lang pala sinabi. If you go back to sa lecture natin last time, nakalagay doon na yung FPJ natin o yung FPI natin can be approximated as 10% ng FPJ natin. Okay? So kung ipakita ko dun sa libro ni Nawi, no? Let me open lang yung libro ni Nawi. Ito, kung babasahin niyo yung libro ni Nawi, no? Along dito sa elastic shortening, nakalagay dito, it is possible, i-highlight ko, no? Yan, it is possible to use the initial value of pre-stressing before transferring equation 3.2 and 3.4 or reduce it by 10% for refinement if desired. Okay? So, itong notation na to, kung mabasahin to. Okay? Kaya dito tayo nag-base. Yes, pagkuha ng PI. Ang PI, pag dinivide mo ng area, equals yun sa FPI. Kasi ang FPI ay stress. Load divide mo ng area is stress. So, PI divide mo ng area, magiging siyang FPI. Okay, so wait, pakita ko nga. Nalilito. Balik ka sa stress formula, no? Okay. So, si stress natin, okay, ang itatanong mo is si FPI. Okay? Si FPI equals yan kay P sub I over sa area ng pre-stressing stand natin. Na si PI equals sa 0.9 ng PJ all over APS. I-check mo yung formula na to kung mag-equal yung value mas makukuha mo dito sa value na to. Okay? So dito, kunin na nga natin. Ayan. Ito yung value, 312,303.6, no? So, 31, may short-term memory lang ako. 312.303. 312,303.6 all over yung area nung ano natin 12 times 0.153. Okay? So multiply, that will be 170,100 FPI, which is also equivalent to okay? Kaya huwag kayo malilito kapag load, in terms siya ng force, tsaka in terms siya ng stress. Kasi pag sinabing stress, dinivide mo lang siya ng area. Okay? Ayan. So, ayan yung sa first natin. Yan yung total relaxation natin. Pero, for the remaining two, kasi meron pa akong klaseng kasunod, no? Sorry. I'll be, after nung class ko today, i-video ko yung kasunod nito. Yung remaining letter B and letter C natin. Okay? Para laboratory kasi yung class ko ngayon, kaya hindi ko pwedeng i-cancel. So, yung for letter B and letter C, I'll create a video after ng class ko. If you want, you can rejoin, no? Pero hindi na require ng attendance doon. Okay? So, yun yung solution natin for stage 1 natin. Okay, question? Other question? Bukod dun sa question ni Mr. Paz. Okay, so ayan yung first sa transfer natin. So let me check lang the attendance before we go.